Hey, in this video, the goal is to create a smart contract language. Again, Ethereum itself is essentially a massive decentralized computer. It supports the ability to create decentralized applications through the mechanism of smart contracts. To create these smart contracts, Ethereum has its own programming language. So that's the goal of this video, to begin building a smart contract language and to create a way to run code written in that language. And we're going to do it all in lightning quick time. All right, to kick things off, let's get in a coding environment. Head to this Replit link at repl.it/@davidjoseph3/lightning smart contract. Replit is this great online editor and tool where you can write your code in the left pane, execute that, and then see the results immediately in the right pane. By visiting this link, you're going to get your own instance of this file to work with. The first thing we'll create is a new class called interpreter. So call that interpreter, and the job of the interpreter is to execute, or rather interpret, code. So let's create a constructor for this interpreter class. We're going to give each instance of the interpreter class a state field. An instance of the interpreter class is represented by the this object. So to create a state field, directly attach it to the this object within the constructor. The state field is going to be set to an empty object. Now, the job of the state field itself will be to keep track of changes in data as code within the interpreter executes. To help out with that, the state field itself is going to consist of a few things. First, a program counter that starts off at 0, then a stack field that is an empty array, as well as a code field, also an empty array. Next, the main method of the interpreter will be one called runCode. So after the constructor, create a new method called runCode, and this is going to have one parameter, a code array itself represented by the variable code. The first line of this method will be to set the passcode array to the one in the state object. So this.state.code is equal to the code array passed to run code. Then after this line, the actual code should run. The idea here is that we're going to iterate through the code array one step at a time. Each item in this array of code is going to be either a special instruction or a value related to that instruction. We're going to define these special instructions soon, but first, let's set up the actual interpreter code that goes through the code array one step at a time to access the relevant instruction. To achieve this, let's create a while loop. This while loop is going to start at the this.state.program counter, and it's going to continue executing as long as that is less than this.state.code.length. Now I'm going to increase this a little more so it fits. All right. In this while loop, first off, we're going to access the instruction, which is found by going into this.state.code into the code array, and then accessing the relevant index according to the program counter. Now, when building a programming language, the more technical term for an instruction is actually operation code. So instead of calling this instruction, let's call this opcode, which is short for operation code. In this while loop, we'll also make sure to increment the this.state.program counter. After all, we don't want this condition to always be true. We want it to break out of the while loop eventually. Now, the next question is, what are these operation codes actually going to look like? Well, we're going to support 3 instructions to start out with: stop, add, and push. So at the top of the file, for each of these values, let's declare a new constant with a matching variable name. So at the top of the file, first let's declare the variable for stop. It's going to be equal to a string of the same name. Likewise, we'll do one for add, equal to a string of the same name. And the reason these are all in caps is that these represent global values, and when you have a variable in all uppercase, it's easy to distinguish that this is a global value for your JavaScript program. So make sure to have stop, add, and push. Each of these is going to achieve a unique purpose. The stop opcode will complete a program written in our language. The add opcode will sum together 2 values. And the push instruction is crucial, since it pushes a value into the internal stack. With these three instructions, we can already write programs that can add together any number of values and then return the result. For example, if we wanted to add two values together and get the result, we could write a code array that looks like this. So declare a constant of code. First, we're going to provide the push instruction and then say that we're going to push 2. We're going to push next a 3, and then we're going to add the 2 and the 3 together, and then we'll tell the program to stop. All right, to see how this will actually execute in the interpreter, let's see how this works with a visual demonstration. So we have this code array that pushes 2 and 3, adds, and then stops. The first thing that happens when we execute is that we arrive at the push instruction, which pushes a 2 onto the stack since the next value in the code array is a 2. Next, there's another push instruction, and this pushes the 3 onto the stack since 3 followed right after the push. Then comes the add instruction. The add instruction pops the last 2 values off the stack and then sums them together to get a result of 5, which pushes that result back onto the stack. So that's why the previous 2 push instructions were there originally. 2 and 3 needed to be pushed onto the stack so that the add instruction could use those 2 values by popping them off the stack. All right, finally, the stop instruction comes, and this completes the program. When the program completes, whatever the final value in the stack is becomes the result of the entire program. In this case, we have the result of the add, which pushed 5 onto the stack, so the result of the entire thing is a 5. Cool. So let's get this working back in the code. Now that we have these opcodes to work with, well, we're going to need to execute the code within the runCode method based on that opcode itself. To handle this, we're going to have a switch case statement on the opcode value. First up, we have the case where the opcode is a stop instruction. In this case, we want the program to complete. So let's halt all execution by throwing an instance of an error object. For this particular error message, let's say that the execution is complete. Now, normally for a case statement, you follow the code with a break, but since we're already throwing an error, it's a bit redundant at this point, so we don't need one for this case statement. The next case to consider is the push instruction. So recall that this one takes the next value in the code array and puts it onto the stack. So to get the next value in the code array, first, let's find out what that next value should be by incrementing the program counter once more. Then we'll get the value itself by finding it from the code array. So const value equals this.state.code, and then whatever is the program counter value at that point becomes the index of what we want to access within the code array. Finally, we're going to push that value onto the stack. So call this.state.stack.push and push that value. In this case, we do want the break statement to make sure that the following lines of the case statement don't accidentally execute. Finally, we have support for the add instruction. The add instruction takes 2 values off the stack, and it pushes their sum back onto the stack. So let's call the first value A, and this is the result of popping the final value off the stack. We have a second value to get, so let's use the same pattern and call that one B. And that'll be the result of calling this.state.stack.pop. Finally, we'll push their sum onto the stack. So call this.state.stack.push, and then we're going to push the result of A plus B. We do want to break from this case statement as well. So awesome, that completes the instructions. We have stop, push, and add. To make sure that this switch statement is clean, let's also add a default statement that does a break. So it's going to be a no operation for this default case. All right, there's actually one last thing to consider though before we actually try running this runCode function. Indeed, the runCode method supports every instruction, but what about getting the result value once run code actually executes? Well, the result is going to be the final value in the stack when the code execution completes, when it arrives at the stop instruction. So let's actually return that value when the program is complete, which we can recognize by catching this error itself. So let's surround this whole switch statement with a try catch statement. So you can actually collapse using Replit's handy tool at the left. I'm going to make sure that this is nicely indented. So now there's a whole try statement around the entire switch, so that way this error can be caught. To catch it, we use the catch statement, which will catch the relevant error. And in here, since we're catching the execution complete error, well, we can return the final value in the stack. And that value can be found by looking at the length of the stack itself minus 1. So this.state.stack and then this.state.stack.length minus 1. Okay, so that wraps up the run code implementation. Now comes a moment of truth. We're going to execute the code array all the way at the top of the file using this run code method. So head to the bottom of the file and then make an instance of the interpreter class. So that is the result of new interpreter. I'm going to call that instance interpreter as well, but lowercase. Finally, we'll call interpreter.runCode, and then we'll pass in the code array at the top. Now I'm going to go ahead and scroll up and get the code array itself, so that way it's a little more visible. All right, so putting this back at the bottom. All right, so that's nice and all together. And here we go, drum roll. And would you look at that? We get 5 in the output of the Replit console. Great. So Replit prints the result of the final value, or rather final line, that you have in your program within this output over here. But overall, this 5 proves that the run code function has the ability to, well, run code. So we have a working interpreter and the beginnings of now a smart contract language. Again, since the purpose of Ethereum is to support building decentralized applications as a decentralized computer, the core of the system is a smart contract language itself, which is great since we've already nailed down an approach for a smart contract language. In the course, we're going to make this interpreter a lot more advanced by adding more instructions. In addition, we'll add all the necessary components to support the Ethereum-like system we're going for: a blockchain network, a cryptocurrency, specialized data structures, and more. All right, let's move on.